Hello guys. So in this video, we're going to be looking at hybrid search. This is probably one of the most important videos in the entire playlist because this has become hybrid search has become one of the most sort of like the de facto standard when it comes to the strategy that we use to build RAG applications. So you look at the big players like Microsoft Copilot, where it looks at all the SharePoint folders, the documents that uses hybrid search. Even all the way down to smaller products, they also use hybrid search. And the reason why hybrid search is important because it uses a combination of two different strategies. We've already seen the vector search strategy, but in addition to that, it is also going to use the classical older keyword search strategy. So we are going to be looking at how they both work together in tandem, how the disadvantages of vector search is solved by keyword search and vice versa. So that is what we're going to be looking at in this video. We're also going to implement it. So I'm pretty excited, and let's jump into the slides. So first, let us look at the problem with pure vector search. That is what we've been doing for so long. So you can see that vector search is great at understanding semantic meaning and context. Okay, so this is pretty established, but it also has some blind spots that can hurt retrieval quality. It struggles with exact matches. Like let's say, for example, the user is searching for API key authentication, but instead getting results about user login security. And why does this happen with vector search? Because vector search uses embeddings that look at the semantic meaning of a particular sentence or a couple of words. So it looks at API key authentication, and user login security is kind of very similar to, closer in meaning to API key authentication. So that is why this particular chunk is retrieved, right? So this we already know. But what if the user knows exactly what they are looking for? So the user knows exactly what is present in the chunks, present in the documents. They are very clear that they want API key authentication only. So in that case, vector search fumbles, right? So it can miss important keywords that users specifically mention. And sometimes users know exactly what terms that they want to find. So this is where, the classical older approach of keyword search comes into the picture. And this is called the classical approach because back in the 2000s, Google search engine, they used keyword search. Even right now, Amazon, search bar that we all know, that uses keyword search as well. You can't possibly use vectors there, right? Because we need exact matching. So this is where, keyword search comes into the picture. This along with vector search is going to give you hybrid search, which is going to be a lot more accurate. Your RAG application's accuracy is going to go through the roof. In the last couple of projects that I've worked in, I predominantly worked with pharmaceutical documents, and the amount of jargons, technical jargon keywords like complex drug names and stuff, that could not be identified by vector embeddings alone. So I had to use keyword search, and my accuracy went. My RAG application's accuracy went like at least like 70% up. So that is the power of hybrid search. Let's look at this classical approach. So keyword search looks for exact word matches in your chunks. It's been around forever. Think Google in the early 2000s. It is super reliable for finding specific terms, names, model numbers, and technical jargon. But at the end of the day, it is still dumb because it doesn't understand that car and automobile mean the same thing. We know it is the same thing, embeddings know it is the same thing, but keyword search is pretty dumb. So this is a drawback of keyword search, but this keyword search along with vector search, they become a very powerful duo. So now let us look at the algorithm behind keyword search. It's called BM25. I'm not going to go too deep and burden you with all the technicalities and algorithms, but let's look at how it works on a very high level. So BM25 is the gold standard for keyword search. It's called best matching 25. It scores chunks based on two key factors. One is the term frequency. How often does the search term appear in this specific chunk? And then inverse document frequency. How rare is this term across your entire chunk collection? So let's look at an example. So in this example, we have two chunks alone. Let's assume that. So chunk A has this particular sentence. Chunk A has Tesla's revenue growth is strong. Tesla reported record profits. Okay, so this is chunk A. Let's say chunk B has Tesla reported strong results. Now, Let's say we ask a query to the RAG system, and let's assume that this RAG system only has keyword search alone, not vector search. So if the entire query just has Tesla, in that case, what's going to happen is chunk A is going to be given more priority, and that is going to be retrieved than chunk B. And why is that? And that is because chunk A mentions Tesla, the word Tesla, twice. Okay, so why does that happen? Let's go back to the original, algorithm. It uses the term frequency. Okay, how often does the search term appear in this specific chunk? So because in chunk A, we have Tesla, the word Tesla repeated twice, chunk A is favored than chunk B, even though Tesla is mentioned in chunk B as well. I hope this makes sense. This is a very small example. Let's look at the next case. So in this particular example, if Tesla appears in 100 chunks, but Cybertruck only appears in 5 chunks, let's say the query is going to be Tesla Cybertruck. In this case, those 5 chunks get higher IDF score because it is rarer. So this particular thing ties into inverse document frequency. So you can see that, how rare is this term across your entire chunk collection. So let's say the user uses a particular term in their search query, and that particular term is only available in 1 out of 100 chunks. So in that case, that one chunk is very, very important. So we are going to retrieve that. Okay, that needs to be absolutely retrieved. So that is what this inverse document frequency does. So a combination of TF and IDF is going to give rise to BM25. So combined, for let's say a query like Tesla Cybertruck, a chunk with Tesla Cybertruck production beats a chunk with Tesla financial reports. Even though Tesla is repeated thrice, TF-IDF is given preference because Cybertruck is only present in a very few chunks. Okay, because the rare term Cybertruck is more valuable than repeated common terms. BM25 is an improved version of TF-IDF that prevents keyword stuffing and handles chunk length better. Now let's move on to the next thing. So this is why we need both, the keyword search and hybrid search, right? Vector search, we know that it catches semantic relationships and context, and keyword search catches exact matches and specific terminology, as we just saw. So together they cover each other's weaknesses. Think of it as having a smart assistant, in this case vector search, and a precise librarian, keyword search, working together. So now that we've looked at the theory part, let's hop on to the code implementation. It's going to be a lot more simpler than it sounds. And since we're going to be working with LangChain's ecosystem, so to implement this keyword search, LangChain provides a very simple class which lets us just use it and implement keyword search. So you can see I have gone ahead, created a file called hybrid search. So let's look at the first cell. So here I'm importing a few imports. So from LangChain retrievers, I'm using this BM25 retriever, and this is what is important for us, BM25 retriever. This allows us to do keyword search in our entire corpus, in our entire collection of chunks. Okay, this ensemble retriever is basically just, lets us combine vector search and keyword search. Okay, so that is all it does. It's basically like a container, you can think of it, that can, put the keyword search as well as the vector search. And as usual, we need embeddings. Why might we need embeddings? Not for keyword search, we might need embeddings for the vector search side of things. Chroma, again, we are going to be using Chroma, LangChain documents, and then we're loading the environment variables. All right, so let's go ahead and run this. Perfect. And just one more thing, we will have to install this particular package, rank BM25, in order to work with BM25 retriever, because under the hood it uses this particular package. So just to go ahead and install this as well. So coming down, I've just prepared a list of chunks right here. Okay, so you can see that the first chunk is Microsoft acquired GitHub for $7.5 billion, Tesla Cybertruck, Google is a large company. So just very diverse sort of like chunks. So you can also see I have added some irrelevant chunks as well, right? Like Java coffee beans are imported from Indonesia, orange juice sales increased during winter months. It's basically just to understand how keyword search and vector search works. I don't really want to point it to our much bigger vector store because we are just learning in this video. And then coming down, all that I'm doing right here is I'm going to convert all these different smaller chunks into LangChain documents, because if you remember, For the vector database, Chroma, we are using the LangChain's version of Chroma, and that ingests LangChain documents only. So that makes life a whole lot easier since we're inside of the LangChain ecosystem. So I'm going to convert all these simple texts into LangChain documents. So you can see I'm just looping through all the different chunks and then creating a document with page content and metadata. For the source, I'm just going to give some index. Okay, so if I go ahead and let's go ahead and run this and this. So right now you can see we've got a total of 18 different chunks. All right, so now let's go ahead and create all the different types of retrievers. So earlier when we were working with vector search, we only had to create the vector search retriever. But right now we also have hybrid search, and then combined together, we are also going to have the ensemble retriever, which is going to be the combination of both vector and keyword. So that's why I've called it 3 different types of retrievers. So first, let's go ahead and create the vector retriever. So this particular code block we have already seen 100 times. So all that I'm doing is, initializing the embedding model, and I'm providing all the different documents, the LangChain documents that we have created here into this particular, initializing of the vector store. So I'm also providing the embedding model. We're specifying that we are going to be using the cosine similarity, and that is it. So we have the vector store. Now we can easily go ahead and initialize the retriever, set the chunk value. Okay, in this case, since we're not dealing with a very large corpus, I'm just going to set it to k equals 2, and we are going to test it out. Okay, so here's a very simple test query. So if I go ahead and run this, okay, it does not work because we have not run this. It should just take a minute. Okay, done. So if we go ahead and run this, you can see space exploration company. In our corpus, SpaceX is the space exploration company. SpaceX develops Starship rockets for Mars missions. So the first chunk is very relevant, and the second chunk talks about Cybertruck reservations, which is not related to the space exploration company, but that is fine. Maybe we don't really have another chunk in our corpus that talks about space exploration, but we were able to find the answer from the first chunk. So this works pretty good. Now let's go ahead and initialize our keyword search or the BM25 retriever. So it's going to be very simple as what we did right here for the vector search. So all that I'm doing is I'm using this particular BM25 retriever class, and I'm saying from these documents, create me a retriever. So that's what this from documents mean, right? It's the same thing that we've done here. So from this BM25 retriever, ingest all of the documents, give me a retriever. So once I'm done with this, I can say BM25 retriever dot k, access the k property, and then set it to 3. Okay, it could be 3 or 5 or 10 or 2, whatever, but just for the demonstration, I have set it at 3. All right, so now that we have initialized the retriever, now let's go ahead and test it out. So we are going to be invoking this retriever with a couple of different queries just to make sure that it is working fine. So you can see that right now we have just provided the word Tesla. So this is the same example that we saw in the PPTs as well, right? So Tesla, let's go ahead and look at our corpus and let's see what we're going to get. So right here, you can see the Tesla term is repeated in, is present in 3 different chunks. But you know that, whatever chunk that has the highest number of Tesla keywords are going to be prioritized, right? If you look at the term frequency, how often does the search term appear in this specific chunk? Okay, so this is going to be given a lot more value. So going by that logic, we are going to get this particular chunk and this particular chunk, and this is going to be prioritized. So let's come all the way down. And if we go ahead and run this, okay, let's go ahead and run this. Okay, now this has been set up. If you run it, you can see Tesla, Tesla, Tesla. Okay, so this is what we saw. This chunk has been retrieved. And also the other chunk where we saw Tesla was repeated thrice. Okay, so this is going to be a tie. Okay, so I have limited it to 2 chunks. So if I run it again, so you can see all the 3 different chunks that have the word Tesla have been retrieved. But the highest priority, it also ranks it, right? Every single retriever is also going to rank it. So the highest priority was given to this particular chunk, but basically this and this, they're basically just a tie. And then in the last chunk, we have the Tesla word that is repeated only once. So I hope this makes sense. We've also got a few other test queries here as well. So if we use space exploration company, in that case, you can see that we are not really getting the right chunks at all, because we know that space exploration company is SpaceX, but we don't see this mentioned anywhere else because the space keyword or the exploration keyword is not present in any of these chunks. We see SpaceX, but not space. So this is why we say keyword search is a little dumb. Let's come down. We can also try out this other test query. In this case, we are going to get a couple of chunks where it's going to match, Cybertruck right here. So perfect. So far we have set up the vector retriever. So you can see we have set up the vector retriever. We've also set up the BM25 retriever. Now let's combine both and create like an ensemble retriever, like a combined retriever. So coming all the way down. So right here we are initializing the ensemble retriever. We are passing in the vector retriever as well as the BM25 retriever in this retrievers list. So this ensemble retriever is not really just limited to hybrid search alone. It is not really just limited to vector search and keyword search alone. If we have 2 or 3 or 5 other different retrievers, we can put all of that in this particular list, okay, combine it together, and we can also give it weights. Okay, so totally it's going to be 1, right? But since we're using 0.5 and 0.5, in this case, what's going to happen? We are essentially telling the ensemble retriever, give equal weight to both vector as well as keyword search. Okay, so in just a minute, we're going to see how the calculations happen. Since we already know how a reciprocal rank fusion works that we saw in the previous video, picking this up is going to be super easy. So now that we have initialized the hybrid retriever, let's put that in action. Let's go ahead and invoke it with a query. In this case, it's going to be purchase cost 7.5 billion. So what's going to happen? Vector search understands purchase cost semantically. It is going to look through the corpus, the chunk corpus, see if there is any related chunks. And BM25 is going to look for an exact 7.5 billion. So hybrid search should combine both strengths for the best result. So if we go ahead and run this, we should be able to see the first one. We've got the chunk that talks about the $7.5 billion where Microsoft acquired GitHub. And we also have some unrelated chunks because we did, tell the retrievers, okay, fetch at least 3 chunks. So it fetched some irrelevant chunks after that. So you can see that we have the answer right here. Let's look at another example. So in this example, we are going to be using electric vehicle manufacturing Cybertruck. So vector search is going to understand electric vehicle manufacturing, okay, semantically, and BM25 finds exact Cybertruck keywords, and hybrid gets the best of both worlds. So if we go ahead and run it, hopefully you can see Tesla Cybertruck production. So manufacturing is somewhat similar to production. So that is the first chunk, and we have Tesla reported strong quarterly results, and that is somewhat related to this particular query as well. If you want to play around with it, I have pushed the code to the same repository. Go ahead, pull it, and you can play around. And now all that is left is tell the LLM, hey, here are 4 different chunks. Here is the user query. Give me the answer. And that is exactly what I'm doing right here. This code is already something that we wrote in the answer generation file. So I'm just grabbing all of the retrieved chunks from the hybrid retriever, looping through it, putting it right here. And then I'm providing the test query here as well. And then I'm just saying, provide an answer, right? So very simple. Now we should get for this particular query, we should get an answer like, based on the provided documents, Tesla's company performance appear to have improved significantly, right? So that is it for the answer generation. Just one more thing that I want to quickly go over, because this is something that you will come across in real world products where we have these weights right here. So how does these weights work? So this is something that we have, fortunately, we've already learned it. So let's come to this particular slide. So let's assume that vector search retrieves 5 different chunks, okay, hypothetically speaking. Keyword search retrieves 5 different chunks, hypothetically speaking. So let's look at, the formula for reciprocal rank fusion. So earlier in the previous video, the numerator was always 1, right? So we did 1 divided by 60 plus 1, 1 divided by 60 plus 2, 1 divided by 60 plus 3. That's what we did. But now we can actually give some weights. So here we are giving the weight as 0.7 for vector search. So that is exactly, we can change it like this, right? So we can do 0.7 for vector search. So in that case, all the numerators are going to have 0.7. Keyword search is going to have 0.3. Accordingly, the balances, the weights are calculated and the final rank is prepared. So in the future, when you get a huge upgrade in your job, in that case, or if you are building your own product, if you are starting up, in that case, all this knowledge is going to come in handy. So again, so far we've just worked with toy LangChain projects, right? LangChain Jupyter Notebook, but there is going to be a slight. I mean, all these concepts are still going to be relevant in production, except we are going to be dealing with scale. So for example, we have a few docs right here. But in the previous project that I worked on, where I consulted with, the amount of documents that they had was in the order of 10,000 or 20,000. So in that case, you're not going to be retrieving three chunks from the vector search and three chunks from the hybrid search. But in reality, you're going to be retrieving 30 chunks from vector side, 30 or 50 or 60 even from keyword side, right? So those are the amount of chunks that you're going to be retrieving. Okay, I hope this makes sense. You're going to be retrieving 50 different chunks from vector search, 50 different chunks from keyword search. So even in my product OpenSlate, which I showed you a demo of a few videos ago, in that product, I have this one strategy called multi-query hybrid search. So let's think about what that means in a minute. So one particular user query is going to be converted to 5 different variations, and each particular query variation is going to go off and do its own hybrid search. Okay, so we know that each hybrid search, when we're dealing with really complicated, a countless number of documents, we will have to fetch 50 different chunks or 30 different chunks for each particular type. So in that case, the vector search of the first query is going to have 50 chunks. The keyword search of the first query is going to have 50 chunks. And then we are going to merge it using reciprocal rank fusion. I know it's getting complicated. And similar to that, we have 4 other different query variations, right? So the first query variation has a total of 30 chunks. The second query has a final of 25 or 30 or 35 chunks. And then at the very end, we again do RRF. Because if you remember from the multi-query video that we did, even for each and every single query, we did RRF. So we are going to do another layer of reciprocal rank fusion. So even then, at the end of it, we are going to still be having 30 or 25 or 40 different chunks. So this is how scale operates, but there is some limitation, right? So we can't really send all these 30 chunks to the LLM along with the user's question, because obviously 30 chunks could be a lot of chunks. The LLMs are not going to be able to handle it. So again, we will have to reduce it to top 5 or top 10 chunks. So how do we do that? So how can we further simplify it? We can do that by learning something called reranking. So this is going to be the final piece of the puzzle. Okay, we are almost nearing the end. So please, pay attention, right? So let's forget about re-ranking for a second. Let's try to recap what we've done so far. So let's say we've got a user's query. The user's query is let's say what is the capital of France, and then what we've done in this video, we've done hybrid search. So that is what we have right here, multiple retrievers. So this dense is just another way of saying vector search. Sparse is just another way of saying keyword search. So using both vector and keyword, okay, we are doing hybrid retrieval. Okay, so this is going to be step 2. We've already done this. Now, step 3 is going to be individual rankings. The retrievers take care of it themselves. So individual rankings, each retriever ranks documents. Okay, so this we don't have to worry about it. What this means is that it's very simple. Vector search, this particular retriever retrieved 50 different chunks. So it gave us in a particular order, right? So this particular retriever thinks that chunk 1 is the highest relevant chunk. Chunk 2 is the second highest relevant chunk. The same thing for keyword retrieval as well. So that is what it means right here. Each retriever ranks its own chunks. Okay, so now what do? We do this process called reciprocal rank fusion. We've already seen that in the previous video, where we are going to combine the rankings using RRF. So that is exactly what we have right here. So we are going to take this 50 chunk, we are going to take this 50 chunk, and then we are going to do RRF. In that case, there might be some duplicates and there might be some chunks that are repeated twice. In that case, they are going to be ranked. Okay, so if you want to brush up your memory, go ahead and watch that video. So far we have this reciprocal rank fusion algorithm sitting right here that is going to ingest all these things, and let's say hypothetically it gives us 30 different chunks. Now, what is the next thing? We cannot send this entire 30 different chunks to the LLM with the user's query to generate the final answer. Why can't we do that? Because 30 chunks are a lot. It might overload, it might go outside of the context window, and also it is a little expensive because the LLM has to process a lot of tokens. So that is also not going to be an option. We will have to only fetch the top k chunks or the top 5 chunks. So we can achieve this by using something called a re-ranking model right here. So this re-ranking model is actually an intelligent model. Okay, it is not as dumb as a simple algorithm. It is an intelligent model. Okay, it's not an LLM. It is not as costly as an LLM. It sits somewhere in the middle. So what that does is it looks at the user's query. It looks at all these different chunks. It looks at the user's query. It looks at all these different chunks. Okay, and then it is going to rank the chunks that it thinks is most relevant to the user's query. So it's going to look at the entire 30 different chunks and it's going to rank it properly. Okay, so the third chunk is a lot more similar to the user's query, so it's going to move it to the very top. So that is why it is called a re-ranker. It re-ranks all these different, changes the order of the 30 chunks. So now this, you can think of it as like an extra filter to the chunks that we have retrieved at the end. Okay, it's an extra filter. We are going to re-rank it, and now we have re-ranked it. We can confidently just go ahead and pick the top 5 or the top 10 chunks. So that is what we are going to be looking at in the next video. I hope I did a good enough job of explaining this. So this is what this re-ranker does. We are going to be deep diving into what re-rankers are. We are going to be looking at a service called Cohere. We're going to be looking at different types of re-rankers that have been trained for specific things, like we've got legal re-rankers or medical re-rankers. So that is going to be the final piece of the puzzle. So I hope you learned a lot in this video, and I will see you in the next video.